So today we're talking about series and sequences. So if it's an infinite sequence is one whose domain is a set of positive set of integers such that a sub n, a sub 1, a sub 2, a sub 3, all the way to a sub n are the terms in the sequence. And a sequence that is finite is only the first n positive integers. So a better way to think about it is a sub 1 is called my first term, a sub 2 is my second term, a sub 3 is my third term, and so on, all the way to a sub n. This list has an order to it. So really all the sequences is a list of things in order. And if it's infinite, it goes on forever, and if it's finite, it stops. Each one of these things in the sequence is called a term. So let's try an example. I want you to write out the first 4 terms of the sequence given by the equation. So an easy way to think about this is I'm going to plug in different n's, and it says the first 4. So I'm going to plug in 1, plug in 2 for the second term, 3 for the third term, and 4 for the fourth term. And this is a sub n equals 3n minus 2. So I plug a 1 in, and I get 3 times 1 minus 2. That's 3 minus 2, which is just 1. So my first term is 1. Then I do 3, and I make the n become a 2 minus 2. 6 minus 2 is 4. That's my second term. 3 times 3 minus 2. 9 minus 2 is 7. So my third term is 7. And then 3 times 4 minus 2 is 12 minus 2, which is 10. So my fourth term is 10. So my answer would look like 1, 4, 7, 10. The next one says it wants to write out the first 4 terms of the next sequence. So n a sub n equals 5 plus negative 1 to the nth power. So I want to find the first term. I'm going to plug in a 1, so 5 plus negative 1 to the first power. Negative 1 to the first is negative 1. 5 plus negative 1 is 4, so my first term is 4. Second term, 5 plus negative 1 squared. Negative 1 squared is 1. 5 plus 1 is 6. My second term is 6. Third term is 5 plus negative 1 to the third. Negative 1 to the third is a negative 1 plus 5 is a 4. Fourth term is 5 plus negative 1 to the fourth. Negative 1 to the fourth is a positive 1. 5 plus 1 is 6. So my sequence would be 4, 6, 4, 6. This is called an alternating sequence because it goes back and forth, back and forth. Okay, so let's try out this next one. We're going to go in the other direction. This time you were given the sequence list of terms, and now you need to find the pattern. So the first hint that's given is that you should ignore the negative. So let's just look at 2, 5, 10, 17. So you can do what's called the differences. I'm going to do 5 minus 2, which is 3. 10 minus 5 is 5. 17 minus 10 is 7. This is called the first differences. And because those aren't all the same, it's not linear. If they were all the same, like 3, 3, 3, then it would be a linear function. We'd write something like y equals mx plus b. So let's try second differences, which means we take these and subtract 2, 2. This is called the second differences. They are the same. So whatever we write is going to have something with like an n squared because we took the differences twice. So we're going to have a second power. So knowing that, we can go over here and let's look at n squared. If I do 1, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. If I compare these numbers to this and this are one number apart. This and this, not including the negative, are one number apart. This and this are one number apart. And the 16 and the 17, not including the negative, are one number apart. So my formula should look something like a sub n equals n squared. Then I want to add 1 every time. But that doesn't address the negative. So we're going to have n squared plus 1. Now we need to address this negative. So I'm going to do negative 1 with parentheses around it. And I'm going to raise it to the n plus 1 power. If I raise it to just the n power, when I did a sub 1, that would make this become a negative 1. I don't want my first term to be negative. I want the second term to be negative. So sometimes when you can't figure out what the pattern is, it's not adding the same amount, it's not changing, like multiplying by 2 every time or multiplying by the same amount every time, using this first, second differences, you can keep going and do the third and fourth differences is very helpful. So in the next one, we're not adding the same amount because 3, 4, 5. So that's what I just did was really the first differences because that difference is 3. This difference is, oops, not 3, sorry, not 4, it's 5. This difference is 5. This difference is 7. So it's not adding the same amount. 0 times nothing will ever get me 3, so I can't multiply. Let's try second differences, 2 and 2. And again, the second differences were the same. This number right here is the same, so that tells me I need a something squared in my formula. So I'm going to have an a sub n in my formula with some kind of n squared. So if I do n squared, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. I'm going to compare that to these numbers. 1 and 0 are 1 apart. It's 1 less. 4 and 3 are 1 apart. 9 and 8 are 1 apart. So my formula is going to be n squared minus 1. So all of these formulas on this page are called explicit formulas. What an explicit formula does is that whatever term number you want, you plug that in. So n equals your term number. 1, 2, 3, 4, 5, 6, whatever it is. And to find that term, so if I want to find the 10th term, I just plug in 10 for n, and that will get me the 10th term. So it's clear cut, very explicit that if I want the 6th term, you plug in 6. Let me go back. On the next page, this is one of the most famous recursive formulas, but we can define sequences as in a recursive manner, which means they are based on the things before them. I may need 1, 2, 3, 4, or more of the terms before me. So Fibonacci is one of the most famous recursive formulas. So Fibonacci actually starts with a 0th term. He tells me my 0th term is this, 1. My first term is this, 1. And then here is his formula. And so what this formula says, it says if I want to find the nth term, I take a sub n minus 2, 2 terms before me, and I add that to a sub n minus 1, 1 term before me. So for example, if I want to find a sub 3 minus 2 plus a sub 3 minus 1. That means a sub 3 equals a sub 1 plus a sub 2. So what you're doing is you're taking the 2 terms before me. So if my first term was 0 and my next term was 1, my next term would be, I take 0 plus 1 is 1. So here's my 0th term, here's my first term, oops, and here's my second term. So I wanted to find the third term. It says you take the first term, which was 1, plus the second term, which was 1, and that would make my third term, which is called 2. So it's this one plus this one makes that one. Then This one plus this one makes that one. So the next term, I would take the 1 plus the 2 to make 3, then the 2 plus the 3 to make 5, and then the 3 plus the 5 to make 8, and so on. So again, this is called recursive because it's based on the terms before me. So you can read down below all about Fibonacci and where this pattern naturally occurs in nature, but it is again one of the most famous recursive formulas. So let's just make sure that we understand the difference between recursive and explicit. Let's say I have some sequence that's represented by a sub n. Actually, let me write the sequence instead. So let's say I have 5, 7, 9, 11, ... So if I want to write the explicit formula, that again is that I plug just n in and I get the term I want. A sub n equals, so we can note here that I'm adding 2 every time, and I started with 5 plus 2 times n minus 1. I don't want to add n the first time, so when I plug a 1 in, 1 minus 1 is 0, 0 times n is 0, and then 5 plus 0 is 5. That gets me my 5, so that's why I did the n minus 1. That's an explicit formula, because I want the 20th term, I plug in 20. But to get a recursive formula, first you have to tell me, like my first term, maybe my first and second term. My first term is 5, and then my a sub n term is going to equal the term before me, n minus 1 plus 2. Because in this pattern, you take the term before you and you add 2 to it. This is known as a factorial. What a factorial means is that you do whatever the number is, you take all the positive integers prior to that, and you multiply them together. So, for example, if I wanted 5 factorial, that doesn't mean 5. It means 5 times 4 times 3 times 2 times 1. So I took all the positive integers prior to 5 and including 5 and multiply them together. You do need to know that 0 factorial is 1, kind of like anything to the 0th power is 1. So let's expand a couple problems. So for this first one, letter A, 8 factorial means 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 6 times 5 times 4 times 3 times 2 times 1, and then the 2 would be 2 times 1. So 6, 5, 4, 3, 2, 1 cancels out with 6, 5, 4, 3, 2, 1. On top, that leaves me with a 56 divided by 2, which is a 28. So the next one is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That's the 8 factorial, and then 3 times 2 times 1 is the 1 factorial over 6 times 5 times 4 times 3 times 2 times 1 times 2 times 1. 6, 5, 4, 3, 2, 1 cancel out with 6, 5, 4, 3, 2, 1. 2 and 1 cancel out with 2 and 1, and on top you're left with 56 times a 3. $168. Okay, so now let's write a sequence, a list of numbers in order that have a factorial in them. So I want to find a sub 1. It's going to be 2 to the first over 1 factorial. That's a 2 over a 1, which is equal to a 2. A sub 2 equals 2 to the second power over 2 factorial, which is 4 divided by 2 times 1, which is 2. A sub 3 equals 2 to the third over 3 factorial, so 3 times 2 times 1. 2 to the third is 8 over 6, which is 4/3. So the first 3 terms are 2, 2, and 4/3. So now we're going to look at this thing called a sigma. So this letter right here is called a sigma. It's a capital sigma in the Greek alphabet. And in math, we use it to represent the word sum, which just means to add. So what we're going to do is we're going to start at our starting index down here, which is 1, and we're going to stop after we get to 4, and then we're going to sum all the terms in between. So if I plug a 1 in, I get 4 times 1. That's my first term. Then I'm going to plug a 2 in, 4 times 2. And then I'm going to plug a 3 in, 4 times 3. And then I'm going to plug a 4 in, 4 times 4. And then I stop because I got to my stopping index up here. This sigma thing right here means you sum, you add them together. So this means I have 4 plus 8 plus 12 plus 16 for a total of 40. This right here, because I started at 1 and went to 4, would be known as the fourth partial sum. Let's try the next one. I'm going to plug in 3 first, so I get 2 plus 3 squared, 2 plus 4 squared, 2 plus 5 squared, 2 plus 6 squared. Then you add all of the things up. So 3 squared is 9, plus 2 is 11, plus 16 plus 2 is 18, plus 25 and 2 is 27, plus 36 and 2 is 38. And so then you have to add them all up, which adds up to 94. So on this one, we do 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial plus 1 over 5 factorial plus 1 over 6 factorial. 0 factorial is 1, so this is a 1, plus 1 factorial is 1, so this is a 1, plus 1 over 2. 3 factorial is 3 times 2 times 1, so plus 1/6. Plus, this is 4 times 3 times 2 times 1. Well, 3 times 2 times 1 is 6. We just multiply by 4, so 1 over 24 plus, same idea, this is 5 times 4 times 3 times 2 times 1. So we're going to do 24 times 5. 1 over 120. Plus, this is 6 times 5 times 4 times 3 times 2 times 1. So it's 120 times 6, which is 1 over 720. So this comes out to be 2.718. So on this page, there's some special summation formulas that you can review. The last part of this section is learning about series. So the series is the sum of all or part of the terms that are in the sequence. If we sum just part of them, it's called a finite sum. And if we sum all of them, it's called the infinite sum. So example 7 says that for the series, the sum of 3 over 10 to the ith power, find the fourth partial sum. So that means we go from I equals 1 to 4, 3 over 10 to the I power. So it's 3 over 10 to the first plus 3 over 10 squared plus 3 over 10 to the third plus 3 over 10 to the fourth. This is equal to 3 over 10 plus 3 over 100 plus 3 over 1,000 plus 3 over 10,000. Now if you read these fractions, you would say 3/10, which is 0.3, 300ths, 3,000ths, 3/10,000ths. So this is the fourth partial sum. If I wanted to find for part B the sixth partial sum, it's going to be the same thing as above, 3 over 10 to the, 3 over 10 to the I power. The first one's going to be 3/10, 3/100, 3/1000, 3/10,000. And then I would have to add 2 more over here, 3 over 100,000, which is 0.00003. And then there would be another one for 3 millionths. So this would be 0.333333. And C just says find the sum. So there is no ending term. It's from I equals 1 to infinity. That would be 0.3 repeating, which is the same thing as saying 1/3.